if you fail, could you avoid using text from the seminar? It encourages would be the same, but I think we continue. This is just from one alphabet, from one word of alphabet to another.
So, for example, a continuous map from A to the Z to B to the Z. If I see a letter here at cell maybe cell I, all the configurations that have this letter they form a cylinder. They form an open set, so the pre-image should be an open set. And actually, you can prove that an open set has to be supported, has to be a union of cylinders, which is supported in somewhere. So there is a finite U, and you have some kind of local rule which only looks at this word, which is written, and tells you which letter to put here. And it's true for every I.
What is the definition of continuous function?
Not really, we proved this.
Yeah, we proved that this is the base of topology, so the cylinders is the base of the pre-image must be the union of cylinders.
Yes.
But it's obvious.
But okay, it's very nice if it's obvious for you. There is just a little remark to say that you have the pre-image of A is a union of cylinders. You have to take the support, which is the union of the support of these cylinders, so that you take this. And actually you take the union of the support of cylinders that are involved in the pre-images of all the letters. For every letter here, every letter will depend on something. Maybe the open set which corresponds to A here it corresponds to a cylinder like this here. Maybe the open set which corresponds to B corresponds to a cylinder which is bigger. But since there are finitely many letters, it's uniformly bounded.
The support of the cylinder is the places where the certain letters should be. Yes?
Yes.
Okay.
Maybe I didn't introduce formally the word support, but it means this. Yes. Support, the support of the pattern, and you take the cylinder corresponding to the pattern. Are there other questions?
I don't remember if there was something except the definition of continuous and then of the previous section. So we can start with the continuous constant.
If you don't really remember, I think there are the videos, or you can ask also to your camerates, because I'm not sure either. I don't really remember what we did in that one course. But at the end of the last course, we just started something more or less new, so we can go back to this. I asked the question, so you are given a graph VE. So
about video.
It's not on?
I think so.
I thought because I can see myself. There is something that moves here. Dynamically. So the graphs I'm interested in. The graphs I'm interested in are finite, and I allow loops. They are directed. I allow loops and I allow multiple edges. So formally, there is a map S, like source, from E to Z, and T, like target, from E to Z. And you can represent these graphs by a matrix if the vertices are taken to be numbers from let's say 1 to n. So there's a square matrix which is associated to this kind of graph. Can you see what? So maybe someone can tell me on this example. Let's say this is 1.
1 or minus 1 depends on direction.
Okay, there are several possible ways of representing, but the easiest one is even simpler than what you were saying.
Just put 1 if two points, I don't know how to say, points.
Number of bars.
Vertices.
Vertices are connected by edge.
Yes.
Maybe we should put number of bars because we have multiple.
Exactly, yes. So you are both right, but here we have multiple edges. So can someone tell me what's the matrix here? So 1 is related. So 1 is not related to 1. To 2. 2 to 3.
2, 5. 5. 4 to 1. 2, 4, and double 5. 8.
Okay. So last time I asked if I look at the set of paths, so does it mean a path? It means that the target of the next is the source of the next edge. So this is G and this is X and this is G. And I asked you to, at home, to tell me everything you can say about this set with a hint that there are related things with respect to the course to say.
Think like open and periodic.
Klopen and periodic.
Yes.
open. So you're saying three things: closed, open, and periodic. So maybe we can go to
Shift invariant.
shift invariant. Okay. Closed, open, shift invariant, periodic. Don't write this, I'm just writing what you're saying, telling me.
Sure, that is periodic.
Okay,
Periodic means every sequence is periodic.
I don't know, what do you mean by
No,
periodic?
maybe I should say there's just shift invariant.
Shift invariant, okay. Shift invariant and closed
Why it
and
is
open. You don't think it's open?
I'm not sure.
How many of you think it's open?
We're writing these properties for this matrix
For example, yes,
or for everything.
for this matrix, for example. The question was for every, but for an
I
example.
think it is not open.
Mhm.
There's a finite number of forbidden patterns. Okay. Because you only forbid like arcs which are not present in the...
Okay, so
It's closed.
what you're saying is that it's closed.
But there are a finite number of, arcs which are not connected. You don't forbid a finite number of patterns.
Yes, so you forbid a finite number of patterns.
So it's closed.
Closed.
Finite.
You have to be careful. I think I understand what your confusion is. Because the closed sets are defined by a finite number of anchored patterns, which means that you forbid them, that the patterns come with the support on which you forbid them. So I forbid, for example, I forbid, I don't know, 2-5. I forbid the pattern 2-5, but I forbid it everywhere. So as an anchored pattern, I have to forbid it infinitely many.
Closed should be the finite union of cylinders, but this
Yes.
obviously is not.
So I'm sorry, maybe because of my use of the word pattern. So from now on, a pattern is something that is up to the shift, but in the characterization of closed sets and of closed sets, it was so-called anchored pattern. It's for some u finite. But when I don't say anchored pattern, I mean pattern, and this is essentially up to the shift. So when I forbid it, I forbid the whole orbit with respect to the shift. So closed sets are defined by finitely many of those, but if you forbid just one and you're shift invariant, then it means you forbid infinitely many. And actually, you can prove that all shift invariant open sets are dense or empty. Exercise. Shift invariant. set is empty. Again. These are the complements of the subshift. And actually, you can prove that there are G delta terms, for those who know. Commuter sets. Do you know this definition or not?
Yes.
It's an intersection of dense open sets. Maybe commuter. It contains the intersection of dense open sets. So there is this Bayer theorem which says that if you contain an intersection of dense open sets, then you are dense. In good enough spaces, like in compact spaces. Okay, so I'm happy with closed and chief analysis. What is the easiest way to say it? I think you said it. It's defined by finite patterns, which you forbid everywhere. But you even said it even better. You said a little more. Defined by how many finite patterns? Finitely many finite patterns. Because
Not more than n.
yes.
If you have multiple errors, you can...
Yes. Yes. So what are the finite patterns?
Forbidden.
Forbidden finite patterns.
All edges that are not in red.
Yes.
All directed edges that are not.
So
In order.
It should be like pairs. Or, for example,
okay. So that's
2, 1, but
that's
1, 2
really-
is 1, 2 is not forbidden, but 1 is forbidden. For example, in this way.
So last week we also defined another set. It was at the end very rapidly, which was a vertex path, which is maybe what you have in mind now. Okay, so the set of paths, but then now I follow the vertices. Okay, so maybe I think that's what you all have in mind now, and this is also defined by forbidden patterns, and the forbidden patterns are
Pairs of S.
So Z we have 0 on the corresponding in our matrix.
Yes.
On this position.
So you can write it either like this.
Is not in S from there.
Yes. Or equivalently,
can you use maybe start and target functions to describe it?
yes. It's actually yes. So
W is not in start from that.
So it's the complement of S it's the complement of the two pairs represented by all edges. It's a complement in terms of V2, you understood? Okay? That's what you have in mind, but in my first question, it's not exactly the same. You see that in this set, we lose the information of the multiple edges. So, it's not, this system is not uniquely determined by, it's uniquely determined by the matrix, but in the matrix there is more information. There could be several matrices which give the same. But here, with this system, it's exactly in correspondence with the matrix if you remove vertices which are useless, like this one. You don't want this because you know that no bi-infinite path will go through it. Or maybe if you're interested in mono-infinite path, at least you want to remove this kind of stuff. So this is also defined by finite patterns, and which are these? It's nearly in the definition.
It's pairs of edges such that start not equal to the target of start of the first not equal to the target of the second.
Exactly.
Now start of the
Okay. So in both cases, what can you tell me about how we can define it? Defined by finitely many forbidden finite patterns. And this means that it is
closed.
it is a closed set, but what I said it doesn't mean it is a closed set.
It is shifting land,
Yes.
and that's why it is closed. Because if we have shifting land set which has finitely many forbidden patterns, it is necessarily closed.
It's assumption.
Yes, good. At first I answer. It's not completely correct what you have in mind. What you want to say is that if you define by forbidden patterns which are forbidden up to the shift, then yes. But closeness, you have closeness and shift invariance are
I understand that.
completely different properties. You have all the possibilities of one without the other. But closed and shift invariant, it means subshift, and it's equivalent to defined by forbidding some finite patterns, but maybe finitely or maybe infinitely many. And here, what do we have? Finitely many. So it is that a subshift can be defined by infinitely many forbidden patterns. So here, thank you. This is a subshift of the two of them. They are subshifts of finite size. And there are even what we call nearest neighbor subshift. Do you understand what it could mean? It means that all the finite patterns are of length 2, or maybe or Markov. Sometimes they are called Markov subshifts. Sorry? Yes, you were reading.
Markov chain, no?
It has a link with Markov chain, yes. What is the link with Markov chain? So,
coordination in Markov chain is determined by just one element, by one state, previous state.
exactly. Exactly. So you don't have a very long memory in the Markov chain. And basically you have this graph. In the Markov chain you have probability to go to the next vertex. Here we just forget about the probabilities and we look at topologically the set of possible paths which follow this graph, and in particular when you are in this path you can forget all your past to know how to extend. You don't need to remember the whole path, you just need to remember the state, the finite state. So, this is the edge subshift. Sometimes you hear edge shift. Sometimes, for example, in the book by Guillon and Marcus, they say shift instead of saying subshift. It's really the same. And this is the vertex shift. So are you convinced that the edge shift and the vertex shift are always nearest neighbor subshifts?
What's the exact definition of nearest neighbor?
It's defined by a set of forbidden patterns of length 2. It's the same as Markov shift. It's really. So, yes. I think it's easier to remember when you have properties which have a name which means something than when you have a property which has the name of someone. Maybe Markov you can remember because it looks like Markov chain, but sometimes there are many properties that have names of people, and it would be more meaningful to have a name which means something. Okay, so but conversely, can you give me a nearest neighbor subshift which is not a vertex subshift? So maybe you take 5 minutes now and you try to prove that every nearest neighbor subshift is a vertex subshift, or to prove the contrary, or to prove that there is one which is not.
Should the vertex Should the graph be fine?
It's always finite.
What if we take infinite graph? It would be nearest neighbor exception. But it can be infinite. Like,
No, because in the definition of a subshift, I always take alphabet to be finite also. In the whole course, we will have the alphabet to be, which is finite. Now, what you just
it
described,
was about Markov chain, not about Markov subshift.
what you've just described is very interesting. It's a very interesting object, which is called countable state Markov shift. And the theory on this is just more complicated. But if you're interested, we can do a session at the end of the course on this. But yeah, there are also many other subjects which are interesting. So nearest neighbor, the difference between nearest neighbor and vertex. So you have to think about this as really a progression and progressing in the configuration. So I should have erased this. Oh. You have the configurations here, and you want to check that you're in the subshift.
So we can define subshift as the definition of forbidden pattern. Give us all possibilities of graph, all edges we can't put to. If we have a subshift, we have all forbidden patterns.
What are you?
So if we could have a graph, we have all forbidden edges there.
Maybe we can look at the complement of set of forbidden words, and for every forbidden pair, we can, for every allowed pair, we can take a vertex, and then which we probably graph.
Are you trying to build a graph?
Yes, trying to build a graph.
Okay. So first, what is the set of vertices?
It's a complement of
Alphabet.
You're not saying this.
It's a complement of forbidden set.
So one possibility is this, and one possibility is maybe A2.
No, vertices are... No, I think even edges are symbols, because of what I'm talking about. Edges are your alphabet. Alphabet are edges. And vertices are just an abstract set, which connects them. Yes, I mean that... Yes, this is what I'm thinking about, yes. You can't have vertices to be not in your alphabet directly. No, because I'm trying to build edge paths. That's what I'm
edge. Okay, so maybe that's a good point. We'll see this just after. But for vertex path, vertex subshifts, you had a...
We have two views. The first is to define forbidden patterns as the edges and as vertices.
Why is it?
I prefer edges.
Okay, so go on.
Alphabet would be vertices, and edges are all not forbidden patterns. But now, I know both.
And I can write S of VW equals V, and S of V and T of VW.
Why you cannot construct, for example, if you have vertices subshift, construct edges subshift from it, and then from edges subshift vertices subshift. We should prove that both definitions are equivalent of vertices subshift. If you have vertices subshift, then you have edges subshift. So?
You shouldn't forget about multiple edges.
Yes, that's a small difference, but
I think you can overcome it with rotating condition versus.
exactly. So, for a given graph, the vertex subshift and the edge subshift can be different, but if you don't have multiple edges, they are equal. They are not equal, they are essentially one-to-one correspondence. You have to, maybe you remember what is the definition of equivalence dynamically? How do we say? The two systems are?
Isomorphism.
Yes, sometimes some people say this, but we said another word.
Conjugation.
Conjugate, yes. Conjugate. So we can prove that they are conjugate in their own multiple edges. And you also have a good intuition that if you take the edge subshift of so if you take the edge subshift of a graph with multiple edges, we saw that it was nearest neighbor subshift. And if we prove that all nearest neighbor subshifts are vertex subshifts, then we can prove that every edge subshift is also the vertex subshift of another graph. It will. Okay, so let's concentrate on the first question. Vertex subshift. So, is it what remains to do here? Nothing. We have defined a graph. What is the vertex subshift of this? It's exactly what we want to do. So, did I write something like this, like the subshift defined by coordinate pattern F? Did I define this? Okay. So does this graph have multiple edges?
No.
No, actually, it could even be defined by the other formalization of graph where you just have the pair, because this is really kind of ridiculous, this definition of SMT. Actually, you see that every edge is determined exactly by its source and target. So,
It's not an edge.
it's it is not or it is?
It is, but we don't have multiple edges.
We don't have, yes, we don't have, but
we should prove that we can't build any edge exception, no?
You can probably have equivalent graphs.
so
No, because you can
If I
know that vertex, like vertex subject, that you don't preserve information about multiple edges. It's just glue them together. Now, when you're working with vertex subshift, it does not preserve information about multiple edges. So it's like logical that if you take like graph like this and multiple edges and apply this operation, you get graph with like 1 edge between every. It will have same vertex subshift.
okay. But now, if I fix this graph, what can you say about xg? So this was x hat g, the vertex subshift, and xg. What can you say? You more or less all have the idea with respect to x hat g.
Xg is edge subshift.
Yes.
So it can.
So first obvious remark between xg and x hat g. I mean, obvious. I mean,
Sequence of all allowed pairs.
sorry?
Set of sequences
Yes.
from pairs of our not forbidden edges. All set of our.
Now, what are you trying to answer? Want to write verses and edges for X3? Do we want to? What do we want to say about xg now? We want to write it as.
So if I look at this, the subshift xg and the subshift x hat g, in the case where I don't have multiple edges, can they be very different? No, you all have the intuition that they can't. And I told you the word.
Take a pair of vertices and
Make
create
a conjugate.
as a conjugate, and you can use like group. Take 2 verses and take 10 edge.
Okay,
Take 2 verses.
good. So I'm writing what you tell me. So take 2 vertices. So you're defining a map.
Yes, like C0.
C0 of. So
We have pair of. Yes.
So here it's it's a stupid map.
But maybe we need to.
Why we cannot take every sequence from x hat g and then construct sequence from xg?
We are doing this.
Yes, and this map will.
Okay, that's what you are doing. So now I take C of x, I I0 of x I plus 1 for all x and for all I. Okay? So by definition, this is something which applies a local rule, which is the same everywhere. So it's really the picture. Here it's really the picture. I depend on 2 things, and I get the image of this. And I have the same local rule compared to the definition, the characterization of continuous function before. I may have different local rules for everywhere, but here I have the same local rule, which with this pattern gives me the next one here.
Maybe what's vice versa from
It is 2 to turn.
yes. Okay.
Yes, I don't care about this A, I don't know. So here it's into the green, and here it's into the green. Okay? So, what does it mean? That it's defined by a local rule? Bounded radius and a local rule?
It's continuous and shift invariant.
It's continuous and shift event. It's a dynamical homomorphism. So we are kind of happy, but we want more. What do we want?
We want to prove that the image is... What do you want to prove?
What do you want to prove?
We want to prove that
That exists. Yeah.
and this graph doesn't what?
But you said the word before, what we want to prove.
Conjugate.
Conjugate. What is conjugate?
To build an inverse.
Yes. Conjugacy is a homomorphism which is bijective, and by compactness you know that there is an inverse homomorphism. So, can you see the inverse? Can we build the inverse? So the inverse has to also come from a local rule. Yes?
Not just start from S.
Exactly.
Start.
S is from E to D, and you can define, let's say, how am I define it? Maybe psi of x I equals S. So maybe I should write another letter. Okay, so this is another homomorphism. So what we want is to prove that they are inverse of one another. So for all x in, so now I have to be careful in which, so here x was vertically, so to the half. By so sometimes usually I don't write, I don't know what you're used to, but psi obviously means that there is this circle, but I don't write. So psi of xi is equal to s of psi of xi, which is s of xi plus 1, which is xi. So, psi is the inverse, is the right inverse of psi, but don't forget you always have to prove also the inverse. That it also works in the reverse order, because if you don't prove this, maybe you have an injective map, but which is maybe you have x, y, you have an injective map which admits an inverse. Which is inverse, but only on psi, but maybe phi of x is strictly included in y, but you could still have this for some psi. So either we prove this, I think it's the easiest thing, or you prove surjectivity, which is easy also. Maybe this is funnier because it's really
Maybe right instead of x here with light. y1, y2, because it's
Sorry?
maybe can you write y1, y2 as an argument? The vertex, sorry. Maybe can you just write y as edge?
You want to...
But okay, no, it's okay, just maybe can.
So, yes, if you want, we can... Because here we proved it for this specific graph, but maybe you want to prove it for an arbitrary graph which has no multiple edges. So you can say...
But no, it's okay, it's just...
y, the unique edge with f of y equals v, p of y equals w. By the way, you didn't correct me, but you understood that here it's not v2, but it's the set of VW such that there exists an edge, blah blah blah. Maybe, so we should call it E. It's really this set here. Yes, I can write it more compactly, like here. Set of S of E, T of E, where is E, E. So there is at least one edge, and if there is no multiple edge, then it means there is exactly one edge, so this is well defined. And here, is it what you wanted somehow?
Yes, maybe that is because...
So here it's easier, psi of si. No, sorry. It's psi 0. But S of y I plus 1 T of yi. Not multiple edges, it's y. So by the way, I'm confused here. Why did I think I forgot one step here? If you want to go there. Sure. So this phi of xi is Okay. So, to summarize, both the vertex subshifts and the edge subshifts are always nearest neighbor subshifts. They are conjugate when the graph has no multiple edges. And every nearest neighbor subshift is equal to a vertex subshift of a graph with no multiple edges. So, in particular, it's conjugate to an edge shift. So, the nearest neighbor subshifts are exactly the vertex subshifts, and the nearest neighbor subshifts are up to conjugacy the edge subshift. Is it clear? Questions?
It was impossible exercise.
Sorry? Is that?
Impossible exercise.
What?
You asked about nearest neighbor subshifts, this is not.
No, but
That's what it is.
everything I said here is not only the correction of the exercise, but I think from what we said in the lesson before, at least those who were here, you could have understood that there were subshifts of finite type. We have just talked about subshifts of finite type. I was expecting at least this word. Finally came, so it's okay. So, but, by the way, I didn't talk about nearest neighbor subshifts last time. I talked about FFT, but what can we say? Do you think now, when you have a subshift of finite type, is there a way to represent it with a graph? Or do you have an example of subshift of finite type which is very, very different from any nearest neighbor subshift? If the length is pattern is more than 2?
Depends on the forbidden pattern. If you have forbidden pattern of the set 3 or more, it is not vertex subshift.
So give me an example. Yes, it's true.
For example, our alphabet consists of 3 numbers.
So, by the way, I'm not sure I have defined this. Order of an SFT is when you can take the forbidden patterns to be included in A to the K. You know that when you have only finitely many forbidden patterns, you can always make it include all of the same length. It's easier because you may extend the shorter ones to all possible extensions, and at the end it forbids the same. So yes, so an example of order 3, for example. Who is talking?
We have alphabet with 3 symbols. ABC, and for B, for example, when we have ABC.
Okay, so give me a configuration in this subshift. Maybe just a finite part of the configuration if you're impatient.
It's repeated.
Sorry?
Maybe yes, and then repeats like.
Sorry?
And then can cycle it.
Yeah, you can, okay. Okay, good remark. But if I write an infinite word here, I don't show it to you. And then I have, I don't know, I have AC. So I'm telling you that this infinite word is okay with the subshift, finite type. Do you know the ways to extend this, the possible ways, or you need me to tell you? Sorry, I do it again. I want you to write a fully valid word configuration which is in SF, and we already wrote a great part of it, but we don't remember it. It's behind my hand. Do we need to remember it to know how to extend it?
No.
I think we can consider another.
If it's a B, we should know if there is A before or not.
Okay, but how many letters do you have to remember? Two. It's only this. So it's really, this subshift for finite type is really something about the memory you need.
Yes, we can consider another alphabet, and then it will be Markov subshift. But for example, if we consider pairs, A, B, B, C, A, C, and others.
Exactly. So we already defined a function which was called the grouping conjugacy. Did we have a notation for it, Greek letter or something? 5? With a K like this?
No, we didn't have.
Okay, so let's introduce. So, spray K of xi is equal to I plus K minus 1. So, you understand when I write this, you understand it means xi plus k minus 1. Okay? So here we said last time that this is the conjugacy. If you look at its image set, onto its image set, it's a conjugacy. Of course, you have to co-restrict for it to be surjective. So, does this help to formalize your idea?
Yes.
If I would say something after you say your idea that doesn't help, it's strange. So,
I cannot explain it in English.
in Russian? Okay, say it in Russian. But, you can.
If we should remember only K last numbers, if we consider this alphabet, then it will be obviously Markov shift, because it is not necessary to remember previous letters from our alphabet.
So,
we can consider our example ABC and
yes. So this has order 3. And what if you apply now 5, 2, not XF. So I apply this conjugacy to the whole subshift XF. What happens?
Why you consider k equal to the... We can take smaller alphabet, if I'm not mistaken. Because k plus 1 divided by 2. The size of our new alphabet should be... Okay, this alphabet will be sufficient.
So maybe we have a word here. Can we apply, what does it give when we apply this? So, the first letter is the pair AB. Maybe I can write it one on top of the other.
Yes.
The second is BA. Then
ST. CB.
D.
And DA.
DA, and then maybe period. Okay? So now, if I remember only the last letter, I know how to extend it because it's like remembering the last 2 letters of the previous one. So how to formalize this? If S has order K, if you want, then let's take something else, the L grouping of SF has order. We are reducing the order.
Order 2.
Yes, here. So 2 it was in the example when K equals 3 and L equals 2, we get 2.
Okay, yes, K minus 1.
K minus 1, this is when you have
K minus L.
maybe we can do this. Otherwise it's L, maybe L plus 1. But we have to be careful. If L is bigger than K, what happens?
0.
But can it have order 0?
It's still 1.
Actually even 2. You cannot get less than 2 because you always have, because even 5K of the full shift has or is a subshift of finite type with order 2 because you want to be able to check the validity between 2 columns.
Yes.
The only subshift with order 1 is a full shift on some alphabet. Here it's not the case. So has order minimum this with 2. But if you are above 2, you can always reduce. This is interesting.
So it is sufficient to study only a Markov subshift for all finite.
Exactly. What's the formal statement which allows what you're saying?
Formal statement: if we have subshift of finite type, then conjugated to some Markov.
Exactly. So, this is why we're quite interested in these finite graphs and these finite matrices. Because every nearest neighbor is the vertex subshift and is essentially an edge subshift. So every SFT is conjugate to any of the two. So for now we will focus more on edge subshift because it has an interesting property about these matrices that you can multiply. So it's a pity I erased the matrix, but in the matrix of the graph, we said that Mij represents what?
One number of edges.
The number of edges between I and J. So now M to the K Ij, what does this represent?
Number of paths between I and J. Of landscape.
Yes. Okay. So if I write the total number of okay, if I write this, it's the total number of paths. So why am I saying this? Because you remember we were interested in the, for example, in topological properties of subshifts, of dynamical systems in general, and they will have nice characterization on the graph representation. For example, the entropy. We had the definition someday. So the entropy I can. So first of all, there were the language of order n of a subshift is the number of patterns of length m in this subshift. Okay, I start at 1, but since it's a subshift, it's the same to start anywhere, because it's shift invariant. And the entropy is the limit of the logarithm of this number by n. By the way, I think I gave a little exercise of whether this was a limit or not. But it was not a little exercise, it was relying on some lemma.
Wait, is this actually by n or by, it's not, or by n to the power of dimension of,
Yes, so here I'm
here you're working with this
Here since last week, I'm in dimension 1. So this is why I'm taking only, okay, I'm taking z everywhere. So z equals 1. Good remark. Otherwise, you have to restrict here in some shape that grows until spanning the whole grid, and here you divide by the cardinality of this. The important thing is that you expect, if it's the full shift, to have the logarithm of the alphabet. To have something finite but positive. So, how can you get this from the graph? In an edge shift, in an edge subshift. Is there a way to relate this with some things from the graph or from the matrix?
the language in order n is the number of n paths, you know, contains these formulas.
Where is it true? It's true, but there's just a little thing to say. You have a graph.
Yes, but it can have like that, and it should have none that it holds, I think it works.
Exactly. So we can always assume that we don't have sinks or sources. Because we can remove them. We can remove, it doesn't modify the subshift, the vertex subshift and the edge subshift. Is it clear for everyone? Here?
But why we should remove them? Otherwise...
Because here we have a number of finite paths on the graph. And here what we want is the number of patterns that appear in one infinite path.
yes,
You see there's a small difference which can be actually, you don't really care when you take something big because the number of finite paths that end in this will be neglectable. But it's simpler to, you can always assume this, it's simpler to have no vertices which are useless. So this vertex is useless because the set of infinite paths of the graph which was before is exactly the same as this graph. And this one also, it doesn't have an outgoing edge, so it's useless. And here, now there is no sink and no source. If you want by infinite path, you can also erase this. So we can assume every vertex has at least an outgoing and an incoming edge. So if we do assume this, then the number of landscape paths is exactly the number of patterns which appear in infinite paths. So can I give you an exercise which is a bit of research, maybe on, I don't know, maybe either in a book or on the internet. So you see that this, sorry, I saw some heads nodding, so I took that as a yes. So you see that this is the limit of
So this limit is always exists.
yes. It exists if at least in V to the D it exists. I don't understand, but in V it exists also. It exists and it's equal to the infimum.
Could you remind what we denote as sum of M, I, J to the K? The third line.
Yes?
Yes. So what?
So M is a matrix,
Yes.
and you put the power K,
Yes.
and you take all the possible entries in this matrix of power K, and you get,
Yeah.
let's choose this, and you get the number of landscape paths. So this is equal to the logarithm of
The value.
yeah, maybe rho spectral values. But I don't want to do the proof now because it's 15 to 9. But exercise proof this. Maybe you don't manage by yourself. So here is a keyword. Theorem. Theorem.
What's the answer? It's E log E to the power.
Sorry?
No, so we say it's like logarithm of E to the power spectral radius of M, yes?
Нет, это просто зависит от собственного числа, но большого.
Now what does this letter mean? It's like E here.
No, it's a rho.
Ah. Oh, this just wait.
It's the usual letter for the spectral radius.
No, it's okay, just want you to
Spectral radius is the maximum modulus for an eigenvalue, but in this particular case where you have matrices with integer non-negative values, entries, then the spectral radius is actually an eigenvalue. Another topological property that you can read on the matrix is transitivity. Can someone recall to me what it means?
Did you define it?
Well, I think we said several times. Yes. I think at the beginning I told you in topological dynamics, among the first two questions that you asked about the dynamic.
That was it.
Yes, event orbit. And then I think we mentioned what it meant for a subshift, for a one-dimensional subshift. What does it mean? What does it mean to have a dense orbit in a subshift?
To define a closed set?
Sorry?
To define a closed set? No?
So the closure is yes. Every finite pattern appears in one single configuration. Why is it true? In 2 words, what makes this true? It's just the base of the topology by cylinders, and you say that dense orbit has to go in all open sets, so it has to go in all cylinders. Okay? So, if I give you a graph, will you be able to say more or less whether it's transitive or not? This one, yes?
There is a cycle, Hamilton cycle, I don't know.
We can.
Hamilton cycle.
And this one?
No.
So when is there a Hamiltonian cycle? There is a simpler word for this property.
When we
Sorry?
Something about cycles, but I don't remember exactly.
when we can connect each to it, vertices with path.
Yes? So you said a word which is sorry?
Complete graph.
No, not complete. What did you say? What word did you say?
If we can find for
No, you said another word. Yes,
Strong to connect.
connected.
To connect.
Yes. So another exercise. X, G is transitive. If and only if. So here I suppose that yes, we are in Z. It's transitive if and only if G is strongly connected.
What is the definition of strongly connected?
Uh,
If когда движешься
Да. Я просто не ориентирована что реально.
Да.
Это что именно ориентирована на
So every two vertices are linked by a path in both directions. Okay, so this one is strongly connected?
No.
No, because here,
Yes.
so this is why we say strongly, because there is also this notion of connected. We can see that if we remove the arrows, it's connected, but it's not strongly connected. Okay. And another question. When? So what is the other question we usually ask about topological dynamical systems? Yes. So when? And there? Week. I'm just realizing now that we actually meet tomorrow.
By the way, the same time, the same classroom.
So last time many people arrived late, so I don't know if it's the best time. I don't know. Should we keep the same? Because okay. Everything
Because now Полина is как будто
Absent.
and for her it wasn't convenient to go late to meet later because she has
of course, yes.
yeah. But now she
I can discuss this task
yeah.
next week.
Yeah. But tomorrow it's okay.
On Tuesday.
Sorry,
We can discuss this task next week on Tuesday.
Yeah, and proceed tomorrow with it. That should be following.
Yes, but yes, okay, that's probably what we do, but I have to think what I can do without the answers of this. But yes, no, we can do something else tomorrow. Yes. So yes, so that's yes, that's good. If you answer all of these three questions, it's good. But so the point is that the main point of this lesson is that in one dimension, when you have subshifts of finite type, you have a very nice representation in terms of graph or matrices, and then you can use many tools from graph theory and from linear algebra, which allow you to decide some properties, basically all topological properties that your subshift has, which is very nice. Because when I'm talking about decide, it's like a little ahead of what we're going to do later. But you can see that every SFT is conjugated to a nearest neighbor subshift. If you give me a list of forbidden patterns, then I can write a program which takes these forbidden patterns and do this kind of grouping, and then build the graph or the matrix. So I can write a program which outputs the representation as a matrix of the subshift of finite type, and which outputs then all of the wanted topological properties of your subshift. So, in some sense, these systems are kind of simple compared to what we'll see in dimension 2, but maybe not now, but maybe in some weeks. And yes, this is what I want you to understand about this. Do you have any questions?
Is there generalization if we have dimension not one but for graphs? Can we generalize this graph idea?
Better dimension.
Yes.
Yeah, you see, so no, precisely that's the point. There, you can see, I mean, you can have some kind of representation, but it will not give you
Conjugation.
such a simple representation like matrices where you can multiply to get all finite paths. We will see this later in the course, and basically two objects which are defined nearly in the same way, that is to say by forbidden patterns. When you take one dimension and when you take two dimensions, then you get to a completely different world between the two. Here it's the world of linear algebra and graph theory. But they can't help for higher dimensions. Any other questions?
I've heard about Frobenius theorem and the curse of economics related to Leibniz systems and productive matrices and so on. And so the question is, these fields are related somehow or not? Because
yes.
there was nothing about entropy and so on, just...
But they don't use the word entropy, but in some sense it's the same, it's the same kind of limit that you take, limit or enough, that you take, but with matrices that represent something else. I don't know if...
Is it used somewhere in economics? I don't know.
I don't think they need to talk about subshift of finite type, but I think that the main tools that are behind are really the same. This is used in many cases. For example, maybe we will do a session on substitutions, and it's a completely different ways of building subshifts, but at some point you also deal with this result. This also appears in probability. It appears in many places. So
This theorem is just for linear algebra, nothing else. Just the existence of this graph.
but linear algebra is everywhere.
Yes.
It has a... Do you want to show me the exact use that you do, or do you want to? Because I think it really relies on the same basic thing, which is which has applications in many subtopics of maths. So it doesn't surprise me. I'm not completely sure of your particular application, but it doesn't surprise me.